Alright, so here we have is a physics lesson on friction here. And the most important, there's three very important things you gotta know about friction. Okay, well you don't really gotta know about friction, but there's three things you really gotta know. You really gotta know force equals mass times acceleration. You really gotta understand that. You really gotta understand the coefficient of friction equals the force of friction over its norm. And the most useful tool here that we're gonna learn about right now is a full body diagram here. Okay, so full body diagrams are really simple, they're really easy, and they're super helpful. Okay, let's just make some room here real quick. This tiny eraser I got. Okay. So a full body diagram, they kind of look like this. Okay. This, you can make plenty of them, and they're sweet and simple, right? They help you visualize your problem here. And here's your object, right? It's got its mass, whatever. It weighs like 10 kilograms, doesn't really matter. And what a full body paragraph does is that it shows all the forces being acted upon this object. So if an object is just sitting there, really the only force acting on it would be gravity, force of gravity here. And whenever you push down onto an object, the floor or the ground or the earth pushes back onto the object. And that force is called force of normal. And on a flat surface, these two forces tend to equal out. So let's say this was 100 newtons, right? Since this up here is 100 newtons, force normal also has to be 100 newtons. And when these two forces, since they equal the same thing, they tend to cancel each other out, being zero. Objects just stand there. Now, usually within friction problems, there's always this force of change, right? There's always just something pushing against that object. That might be U, right? Force of U pushing that object, right? FU for short. Now, if you push against that object, there's something called friction here that pushes against you, okay? And it always does that. It's always going to push against you when you're pushing an object. I mean, with wheels, it might make it easier, but if you're going to push like a desk I got here, it's going to be very difficult. So force of friction pushes against you, and you push against friction. The most important part of solving friction problems is the force equals mass times acceleration formula. Now, whenever we talking about whenever you use this formula, mainly with force net, or the net force. And the net force is the culmination of all the forces being acted upon an object, right? So there's maybe force of U, pushing the object. And there's force of friction pushing against you, pushing the object. You know what I'm saying? And then there's also force G, which pushes down, force of gravity, which pushes down on the object, and force norm, which counteracts that force. But since it's on a flat surface, you don't really have to care about these two forces. That's supposed to be force norm, not force of G. You don't really have to care about these two forces because they like cancel each other out, right? They counteract each other. The main focus is on these two forces since they tend to be different. They tend to not really counteract each other. Like this could be 120 and this could be 60, and the F net, since they're moving against each other, you don't add them together, they're like subtracting. You could add them together if this was like, since this is technically a negative, but you mainly it's mainly subtraction that's going on, you know what I'm saying? So then you'd add them together and they would be, 60. The F net would be 60, right? Because, 120 minus 60 is 60. And then you could also use that to maybe like find the acceleration or maybe even find the mass. You just got to use your algebra. Now, another very important part of solving friction problems is understanding what the coefficient of friction is. Now, a coefficient of friction is unitless, and it helps you, in friction problems, it helps you find the force of friction, or maybe even the force of norm and the force of gravity there. So, and we have the same full body diagram here, which is just, where 100 newtons of gravity pushing down on this object and 100 newtons of force norm pushing back on gravity. And let's just say a force of friction here equals 5.5. All right, so to find the coefficient of friction, we just plug it in to our equation here. Now that's 5.5 over 100. Now this one's pretty simple to do in your head. You just move the decimal point 2 places over, and the coefficient of friction equals 0.055. Easy. Now you could also work backwards while using geometry. Let's say that our coefficient of friction equals 1.2. No, not 1.2, 0.12. 0.12 equals force of friction over 100 newtons. And we're trying to find, of course, the force of friction. So what you do is you use your algebra and multiply 100 to both sides. Therefore, canceling out this 100 and multiplying it to that 100, to 0.12. So 0.12 becomes 12, and 12 newtons becomes 12 newtons. You got to carry your units over here, and 12 newtons equals the force of friction. Simple, it's easy, it's nice. Alright, so since we went over the 3 most important topics of solving friction problems, let's have a practice problem here. Now, the practice problem here says, Trey is pushing a box that weighs 25 kilograms at a force of 500 newtons with an acceleration of 10 meters per second squared. What is the force of friction? Now, when you start off any problem, you always want to draw, any friction problem, you always want to draw a full body diagram. Because full body diagrams help you visualize the problem and help you solve the problem. Now, this problem does not need you to find the force of G or the force norm. We can solve this problem by using force equals mass times acceleration. So since we have both mass and acceleration, we can just fill it out. Here we go. But let's just finish this diagram real quick. He's pushing it at a force of 500 newtons, blah, blah, blah. Okay, here we go. So force net, the entire force here, equals 25 times 10. 25 kilograms times 10 meters per second squared. And that equals, force net equals 250 newtons. Now, to get to 250 newtons, the F net, force U has to subtract against force F, force of friction. And since Trey is pushing at 500 newtons and force of friction is pushing back at whatever units, we have an F net of 250. So to find that, to find the force of friction, all we have to do is use some simple algebra. So let's take this away real quick. Let's put that back. Equals 500 newtons minus Fu. So then we just move this to this side by subtracting 500, move that to this side, here we go, by subtracting 500 to both sides, and we would get negative 250 equals negative Fu, and since they're both negative, Fu equals 250. And this, we can know, you know that this is correct, because since these two forces are counteracting each other or pushing against each other, you'd subtract them together, and you know, when you get 500 minus 250, you get 250, and that also equals our F net here. So the force of friction is 250 newtons. Now, for additional practice, we have a second practice problem. The practice problem reads, Justin pushes another box that weighs 15 kilograms. He pushes the box from rest to 5 meters per second in 10 seconds. The coefficient of friction is 0.36. How much force is Justin applying to the box? Now this question uses all 3 of our important facts about friction. Okay. So first, of course, we want to draw ourselves a full body diagram, because full body diagrams are very helpful. Now the force of G equals 15 kilograms times 10 meters per second squared, using our F equals ma, and that is 150 newtons. And so if force G equals 150 newtons, then force norm has to also equal 150 newtons. Now what we're looking for in this problem is F of U, but we also need F of friction and the F net. But what we're missing in our force equation is our acceleration. We don't have an acceleration, but what we do have is VI and VF. In order to finish our force equals ma formula, we need to find acceleration. But this problem gives us an initial velocity, a final velocity, and a time, which just so happens to be what we need to find to find acceleration. Now, acceleration equals a change of velocity over time. And we know our VI is 0 because the object starts from rest, and VF is 5 because it says it goes up to 5 meters per second. And our time is 10 seconds, yada, yada, yada. So we define the change of velocity. What we do is that we take our initial velocity, we take our final velocity first, and subtract that to our initial velocity. That just gives us 5 meters per second, right? Because it's just 5 minus 0. Now the change of velocity, we just plug and chug the numbers here, and we put our change of velocity over our time, and that'll give us 0.5 meters per second squared, which is our acceleration. So we just put it into our formula here, and we get 7.5 newtons. Kind of running out of space there, but whatever. Now with the force of the net force, we can't really do anything yet, but the problem also gives us our coefficient of friction, which we can use along with force norm to find the force of friction. So what we do is we just, again, plug in the numbers to our coefficient of friction formula. 0.36 equals F of friction over force norm, which equals 150 newtons. So we just multiply both sides by 150 newtons, which will give us 54 newtons equals F of force of friction. So now that this equals 54, and we know that our F net equals 7.5 newtons, 7.5 newtons equals force of Justin minus force of friction. So we just plug in our numbers here again, and 7.5 equals force of Justin minus 54. And we add 54 to both sides, and that gives us 54 plus 7.5. That gives us 61.5 newtons equals the force of Justin. And then this is our answer.